Yes.
All right. So this is going to be the last video that I will make for the semester. This is the last assignment that you will have. The assignment will involve using two different data structures, a stack and a queue, to reverse a song, basically by just taking the actual samples and then putting them backwards in a file. It'll make more sense when I explain it. So first I need to explain each of the different structs that will be used for each class. So the first struct is a node type, and this will be used for one node in the queue. And the way the queue class will work, or stack, sorry, this is for the stack class. The way that the stack class will work is like this. So we'll create one stack, and the stack will be an array of a specified size. And there is a integer top, and top will point to the next index in the array to be written to. So top is empty, and if top points to 0, then this stack is empty. So when you write something to it, and then you move the top so it points to the next index in the array. And you do this as you keep writing. Keep writing, and each time you write to the top, make the top point to the next index. Make the top point to the next index. And when you've written to this final index in here, what you do is this stack is one link inside of a stack. So this array is inside of a node inside of a stack. And when this array gets filled, what you do is you make the link point to a whole new node. This is a whole new node. And it has its own array, which is the same size as the last one, and its own top. And then you write to that top. So the basic function for this kind of stack is that you, for each node, you fill the array, and then when that array is filled, you make a new node, allocate a new array inside the node, and then start filling that array. So this data structure is essentially of chains of nodes. Each node in the stack holds an array of values and not just one value. In the actual stack, data set is the name of the array, and it is going to be a pointer because it is dynamically allocated. So you can create an array of any size. Top points to the index that is at the top of data set. It is whatever is the highest location, and sometimes top can point to above the matrix. It can point above the array. And when it points above the array, that's when you make a new node and then start filling a new array. Now for a queue node, it's kind of the same. So you have the dynamic array. But this time you have a front and a back. And the front points to the front of the queue. The back points to the back of the queue. Let me reverse these. So the front points to the front, and the back points to the back. And when the queue starts out, back and front are both pointing to the same index. So these are also indexes. When you write to the array, you write to back, then you make back point to the next index. And then you keep writing, and you move back up, and then you write again, and then you move back, and it keeps on pattern of you move back up, you write, then you move back to point to the next index. And then you write again, back points to the next index, then you write again, then back points above the index. So when back points above the index, do the same thing with the stack. Create a new array. New front and back. And then right here. And then make back point to the next empty index. Only difference between a queue and a stack is that with the stack, when you read things from the stack, you go from the top down. So let's say we wanted to start reading things. We would say, all right, move top to read this location, right? Then make top point back down. And when we finish reading an array, we delete this node, and then we go back. We say, all right, read again, read this. All right, make top point back down. Read this. All right, top is now pointing to here. Read this. Top is now pointing to here. Read this. Top is pointing to here. Essentially, when you read from the stack, you go from the top and then you start going back down the stack. But with the queue, it's the exact opposite. When you start reading from a queue, you start at the front and say, all right, read what's at the front, then move the front up. Then read what's at the front, then move the front up. Then read what's at the front, move the front up, etc., etc., etc. A queue stores information in kind of the same way that a stack does, but it reads it differently. It reads it starting from the front. Everyone understand how these two data structures work?
Yes.
All right. All right. So for the class linked stack, the constructor takes one argument, and it is int new size. And the new size represents the size of the array in each node. And you need to check that the new size is it has to be in the proper boundary. If it's less than array min or greater than array max, set the size to the array default. And if it's fine, set the size of each array to new size. Set stack top to null pointer and set count to 0. Because when you first create a class, you're creating a stack that doesn't exist. You're not allocating anything for the stack yet. For the linked stack, what you want to do for the destructor is there's some kind of the one that points to null at the end. So for link stack, what you want to do is you want to, starting at the first one, deallocate the array, then deallocate the node. Move on to the next one, deallocate the array, then deallocate the node. Then move on to the next one, deallocate the array, deallocate the whole node. And at the final one, deallocate the array, deallocate the node, and then finally you're pointing to null. So using some kind of temp, you want to keep moving the stack top forward, and each time you move it forward, delete the temp. And keep doing this until stack top is pointing to the null end of the array. Does everyone understand this?
Yeah.
All right. For stack count, just return count, because when you add or delete things, you want to keep track of what has been added. All right. For initialize stack, what you want to do is, if there's already a stack there, you want to delete the stack. And that's very similar to what you did for the destructor. Only difference is that when you delete the stack, you're going to have a stack top's going to be null. You're going to have a null stack. So what you want to do is take stack top, then allocate a new stack, and then a new data set, and then have it point to null. Have top point to the first index. So this initializes the stack and gets it ready to start printing information. Now for isEmpty stack, there's two conditions. If stack top is null pointer, that means that the stack is empty because the stack hasn't been allocated. But if stack top exists, if there is a node, but the node points to null and the top of stack top points to 0, that means that the node has been created, but it hasn't been filled. So there's a node there, but there's not any data in it. So if this condition is true, that also means that there is an empty stack. Now for the top, that's relatively simple. If the stack is empty, just return 0 because there's nothing to be read. Else, you want to return the current stack top, the data set. This looks kind of complicated, but it's basically, here's the stack top, here's the link in front of it. Sorry, technically behind it because it's a stack. So this has been filled. This is the current stack top. So what you want to return is the data at the top of this stack. So you want to return the data that's at the stack top, but specifically at the top of this array. So because top points to what's supposed to be an empty index that hasn't been written to, you want to return data set at stack top -1. Does everyone understand? All right. Also, as a note, the top function should not delete anything. It does not remove anything from the stack. It just returns the top of the stack. So push should first check if stack top is a null pointer. And if it is, it should initialize stack. So the first thing you want to check is if you have an empty stack. And let's just, for example, say you don't have an empty stack. Everything has been written to. And top points above the array. So if stack top, this, stack top top, equals the size of the array, you want to create a new node. So this is the current stack top. And you want to create a new node. And you want to allocate an array. And you want to start its top pointing to the bottom of the stack. Then you want to make this point to the previous one because we want the stack to be read in reverse. You make this point to the stack top, and then you make stack top point to this. And then you can start writing data to it. Everyone kind of understand this basic process? Or does everyone basically understand the process, is what I mean? All right. So for pop, first thing you want to check if his stack is empty. And if it is, just return. And the way that we kind of deal with deleting something is we don't actually delete anything. We just move the index down. So stack top points to here. Because this is where the data is going to be written to next. So when we want to delete this, we don't actually do any kind of deleting. We just make the stack top point down. That's effectively saying this has been deleted because now it's in the space that the stack will write to next.
Oh, so you're saying instead of deleting, we're just overriding what was previously there?
Yes.
Okay.
And if it just so happens that you, when you delete it, you end up deleting the last thing, like here, what you do is you make the stack top point to the previous link, and then you delete this. You delete this array, and then you delete the node. So the whole node has been deleted once the last index has been deleted. And at the very end of the function, you decrement count. In fact, I want to make special mention that in the push function, I forgot to mention this, but it's very important. At the end of the push function, you want to increment the current stack top, and you want to increment the count. If you increment the count, this way you can always have an accurate count without having to manually go through each node and count each time you wanted the count. Does everyone basically understand how the push and pop work?
I'm just curious, how would you increment the stack top?
So stack top is of type node type. Do you remember talked about how this is going to make up this is the struct that makes up the different parts of the stack. Stack top is going to be one of these. Does that answer the question?
Yeah.
Now that is it for the the stack class, now we go on to the queue class. So creating a linked queue, the constructor is basically the same. You want to make sure that the new size is within the proper minimum or within the proper max, and then set it to the proper value. Then you want to set the queue front and the queue rear to null pointer and set count to 0. So for this one, there's two different pointers. Let's call them QR, QF, and QR. And they basically point to the current rear and current front. So the front is where data gets read from, and the rear is where data gets written to. So the front will point to the first node, and the rear will point to the last node. And when you first create the array, though, you want them both to be null, because you don't want to create the queue just yet. So for initialize queue, you want to do kind of the same thing that you did for the stack. So let's create an imaginary queue chain. Put the dataset array. So the way to delete it, the entire chain, is very similar to the stack. You want to grab onto this, then move queue front up, then delete the array, then delete the node. Then grab this, then move up again, then delete the array, and then delete the whole node. Grab this again, go forward again, delete the array, and then delete the entire node. And then once again, move the queue front forward, delete this, delete the array, and then delete the entire node. And at the end, queue front and queue rear both point to. I should have added a little note in here to say you should also set queue rear to null pointer. Just as kind of like a safety measure. But anyway, once this has been deleted, and you now have a queue rear and a queue front that point to nothing, for initialize stack, you want to create a new node, you want to have queue front and queue rear point to it. Then you want to create the dataset array. You want to set front and back to 0, so they both point to the first index. And then set the link to null. So you have one node that initializes the array. Does anyone having trouble figuring out what exactly I just said? All right. For queue count, you also just return the count. Now for the destructor, It's the same thing for the initialize stack. Only difference is that in the constructor you would leave everything at null. So you delete the queue, set queue front and queue rear to null pointer once everything is deleted, and then that's the destructor. So for is empty queue, there's two conditions. If queue front is null pointer, then return true, because the queue doesn't even exist. Now, if queue front and queue back are both the same index, queue front and queue front back, meaning that at the front, the back and front nodes point to the same location, that means that the array is empty because this has all been written to and it has been read as well. So they both point to the same location, meaning everything below this has been both written to and it has been read. So this current point is empty. Nothing's been written to it. There's nothing to read from it. So if queue front equals queue front back, then return true because there's nothing to read. Essentially, it's empty. For the front, you want to return the current front of the queue. And once again, like with with getting the top of the stack, you're not deleting anything. You just want to return the data. If the queue is empty, return 0 because there's nothing to print. And what you want to do is you want to return the queue front data set at the front. Meaning you want to turn the current front of the entire queue. Does anyone confused by how I just put that? All right. So for adding an item to the queue, first going to start with back. So with returning the back, if queue rear is null pointer, return 0. And you want to return the last written to data set, which is at the data set at queue rear at back -1. So back is pointing here, but you actually want this. You want the last thing that was written to. Because for all intents and purposes, back points to an empty cell. So for add item, you want to first check if queue front is null pointer, and if it is, then initialize queue. So let's start out and let's assume that we are at a node that has been fully written to. So back points above the array. So what we do is we set the rear link to a new node. And then once we have this new node created, we point queue rear to the new node. And we set the link to null pointer Then we allocate the data set. Then we set the back and front to point to 0. And now that we've allocated our new array in the case that we want to write to a queue that has been filled, now we can set the current back of the queue. We can take this, fill it with data, have back, point to the next empty cell. And also we increment count. So that way we are keeping track of how much we have added to the queue. Anyone confused by what I just said? All right. So for delete item is pretty simple. If the queue is empty, just return. And the way that you delete an item is that you take the current front of the queue and you just move it forward to say that this has been erased from the queue. It has been dropped from the queue. And if, let's just say that we've quote unquote erased everything inside the array, what we'd want to do is we want to get a hold of this and then make the current queue front point to here. Then we delete all of this. We deallocate the array, deallocate the node, and that deletes that and moves the queue front ahead. And then after all that, we decrement the count. So for print queue just prints everything in all queue in the entire queue node system. So you'd have a double loop, one which loops through each link in the list, and then an inner loop for each link where you start at the front and then you loop all the way to the whatever the current back is. So the outer loop would be you loop through the nodes in the array, and the inner loop is you loop from the front through each index up to the back, and you don't include the back. Everyone understand the print? All right. Let me make a new layer. So I'm going to kind of explain what the purpose of the assignment is, so that you really understand what it is you're doing. So you're going to be working with a data file that is basically laid out like this. So you're going to be working with a data file called a .dat. And it's kind of just like an MP3 file or like a .ogg file. It's basically an audio file turned into just the numbers. And you can take an ogg file and you can convert it to a dat. And you can take a dat file and you can convert it to an ogg. But the important thing is, first let me cover these two lines. So the first line is important. It is the sample rate. And it's not really that important. Just understand that the sample rate is used to determine how big the arrays are. And this is not important for the program. It's just important that when you reverse the audio, these need to be the first two lines. That's the big important thing. These needs to be the first two lines in the reversed audio file. Now, here's the important part. So this is basically the timing and the actual value of the samples. So what you need to do is you would need to, let me just do something like this. So you're going to have, this is your input file. And the input file is going to look like this. So what you want to do is you want to take that input file and you want to take this and you want to reverse these so that way you read all of this in and then you print it backwards to an output file so that it looks like this. So that when you take this DAT file and you convert it to an OGG, it will be the reversed audio. So from the top, you convert audio format to this DAT file. Then using your program, you reverse this into this file. Then you convert this using a special program that's just a part of Linux back into an OGG. And it will be the reversed version of the original audio file. And the only part you really need to worry about is just taking all of this, reading all of this, and reversing it. And that's why you're creating the stack and the queue class for this assignment. So the basic kind of flow is you're gonna run the program like this. Period / something. Actually, you're going to want to name it reverse. And then input, output. So there's going to be there should be 3 arguments passed to this program. So if argc equals 1, you want to print an error message and return exit success. If argc does not equal 3, you want to print another error message and return exit success. And the error messages should be in the example main that comes with the assignment. So you want to open an ifstream in file using the argv1. If it failed, print an error message and exit. If it was fine, then open an OF stream using the second, which is technically the third, using argv2. If that failed to open, print another error message, and then exit. Now you want to use a string to get the first line from the input file. And then you want to immediately print that line to the output file. If sample rate, so this string is not a substring of line, meaning that the dat file, whatever file that you have, does not look like this, then you want to print an error and then exit the function, or exit the program. Now, if that's succeeded, you want to erase this substring from the line, and then use s2i to convert line into an integer sample rate. Then you want to just get the next line from in file and print it to the output file. So basically this line of code, or this kind of algorithm here, is just saying, once you have this, the sample rate, and you've printed it to the output file, just get this next line of text and just reprint it to the output file, because we're not going to change anything at all about it. So just copy it over. Now, here's the part where we actually start reading from the file. While you aren't at the end of the in file, you want to read into two different doubles, and then using the queue and the stack, you want to start storing the first sample and the second sample. So basically the two numbers on each line. You want to do that until you've read everything from the file. And then once the file has been read from, this is the part where you print in reverse. So while the queue is not empty, I should clarify, you want to print to the file. So let me fix that. While the queue is not empty, you want to print to the file the current queue front and the current stack top. And then you want to delete the current front of the queue and pop the stack. And you want to keep doing that in a loop until you've written everything in the queue and the stack to the out file. And once this is done, close both files and return the exit success. Does everyone understand the basic idea of the program?
I have a question about this program. Do we need to include the reverse in the Makefile we have to make?
Yes. In fact, I'm going to use an example Makefile that I made for a really small program to kind of show you guys how Makefiles work. And I'm going to do that right after I answer any final questions about the assignment. All right. So here is an example program that I have made. So we have 4 different examples. We have a .h file that contains no classes and contains a few functions. And we have a class that is made of a .h file and a CPP file. And finally, those are all made into a main file. If I wanted to compile these normally, it'd have to be something like G++. Whoops. G++. And that's CPP. Fish.cpp. Fish.h. And fun.h. All right. But that just gives me one. That just gives you one specific file. And even though I only have 4 files total, what if this is a project with 20 files? What if I had 50 files because we're making Windows 11d7? What if I needed these each to compile to different object files that I had to distribute to several different vendors? Well, that's where a Makefile comes in. All right. So a Makefile is basically specific instructions on how to compile everything when you type make. So a big thing about Makefiles is you can kind of use variables in it. So I have this quote-unquote variable declared cc, and it's equal to G++. So when I use a $sign and then 2 parentheses to call cc, that's basically the same as me saying G++. And when I type in, I declared C flags, and I declared it to all of this, to with extra, with all, pedantic, standard equals C++ 11, G, and when I call it down here, that's basically like taking all of this and just spreading it out. So these 2 calls to this gets translated to this when it actually compiles. Does everyone understand kind of how that works?
Yep.
All right. So when you have a Makefile, you need to have an all target. So I'm going to, down here at the bottom, I can technically make any of these targets if I felt like it. I could say make main.o. And when I typed make main.o, it just made the object file for the main. But when you declare all is what gets made when you just type make. So when you just type make, it makes everything. I'm going to start deleting object files to demonstrate something. So when you declare your all, that's basically what gets made by default when you type make. And in the instance of this program, we just want to make main. And I want to specify this name here, main, the target, and this here, what gets compiled, are different. In fact, I could name this to Cowabunga. And if I typed make, even though the target was called main, it generated a file called Cowabunga. So the name of the target of what is to be compiled and the file that gets created are completely different. Though usually you'd want to give them the same name to make it less confusing. So when you have a target, you would need to list anything that is needed for that target. So let's say I'm making main. All right, well, to compile the final executable, I need the object file specifically an object file for each CPP file. So when I say I need to compile the main program, I need to tell this target that we also need these files, or we need these targets as well. And for each of these targets, we would have, with these targets, another list of files that we would need. So for main.o, the object file of main, we specify we need the CPP file for main, the .h file for fish, and the .h file for the random functions. And this command here, this -c, when you add this to compilation, it's saying compile this into an object file. So this compilation command plus C turns this into an object file called main.o. Now for the target fish.o, this compiles the fish class and both the fish h file and the fish CPP file, the whole class, into an object file. Same as with main, we add the command to C to tell the compiler to create an object file out of fish.cpp. Now in the highest level, in the main, creating the final executable, we give it the compiler command and the flags, and then at the end we have the object files that get compiled into the final executable. And then we have this here, -o main. This command at the end of, inside of called the G++, is a tag for what the final file should be named. So this .o is saying to G++, take what is after this and make that be the name of the final executable. So by saying G++ flags -o main, it's saying make the final executable be named main. There's also a special target for makefiles called clean. And clean is basically just a command to clean up extra files. For example, if I wanted to erase everything that had been generated from here and start all over again, just to check something, I would type make clean. I can't really type it here because rm is a Linux command only. But the basic gist of it is for the clean command, you need to code what it is that you want to be removed or what you want to be deleted. So my clean command is just remove any file that ends with O. Basically, remove every object file. Everyone kind of understand where I'm going with this? All right. And one note is that makefiles are very, very peculiar about spacing. So between this space and this space, each of these is a tab, except for in the actual C++ commands. Every space is a tab. So this is a tab, this is a tab, this is a tab. These are not tabs because this is a Linux command. This is tags, this is flags for C++. These are just spaces, but this is a tab, this is a tab. Between here, even though it's one space, it's still a tab character. This is also a tab. I know this sounds kind of weird, but let me, for example, make this be just a space, and then let me type make. Or maybe I'm wrong. I don't know. Make can be kind of finicky, though, is what I'm getting at. So I'm going to show you an example of using a variable, so to speak, in a Makefile. I'm going to delete that. So I've taken main.o and fish.o, and I have turned them into one variable. So when I type make, it still compiled everything, because when it hit this, it went up here to kind of unfurl this and find that, all right, these are the two targets that I need to make. And when it was compiling everything, it went back up here again and then said, all right, these are the two files that I need when I compile. That go by too fast for everyone. All right. Well, I'm going to be available until 4 to help anyone with any questions that you might have. But good luck on the final assignment. Good luck on the final exam. And if you have any questions, feel free to open a ticket or just send me a direct message.